All right, we're going to talk about linearization here, which is the first topic um, of section 5. And in section 5, or within linearization, I want to sort of graphically set up what we're um, what we're doing with linearization. So let's start with just some arbitrary curve, y equals f of x. All right, and then we'll pick some point on the curve, and we're going to call it it's going to be at x equals a. And we'll call this point a comma f of a. Right? And so let's actually zoom in a little bit here. So I need to have this extra space. All right, so what we're going to do, well, actually, let's think back. When we first talked about differentiation, before we even talked about it, we did a lab called zooming in. And in that lab, what we did is we took a curve, and at a specific point, we zoomed in really far until we, what I called linearized it. In other words, we zoomed in so far that it became a line. All right, and we said, well, if we take the slope of a secant line, so we pick 2 points on that zoomed in segment of the graph, that's a pretty good approximation for the tangent line. Most of you agreed. What we're doing with linearization in this section is we're going to say, all right, well, if we can get the tangent line, then we can get a pretty good approximation for the function value near that point that we're analyzing. Okay, and I'll show you graphically with Desmos here in a minute what I mean by that. But the idea here is, let me finish the sketch. So I'm going to sketch in the tangent line through a f of a. And the equation of this tangent line is y equals the slope of the tangent line at a, which is f prime of a, times x minus a, I'm just using slope, point slope form, plus f of a. That's the y value, okay? So point slope form, using the derivative, that's the equation of the tangent line. I can use that tangent line to approximate function values. So let's move over to the next box here. The moral of the story, we know an approximation of the tangent line can be found by evaluation of slopes of secant lines very close to some point a comma f of a. It turns out that we can also approximate a function value at x equals a, or near it, using the equation of the tangent line. I really should say near it. When the tangent line is used in this way, it's called the linearization of f at x equals a. And the book will use L of x to denote the linearization. All right, and they always put the f of a first. I don't know why, but you can see that this is just the equation of the tangent line from the left. Okay. So when they ask you for the standard linear approximation, what they're saying is, and what we're saying is that the function value at a, whatever the function value is at a, in other words, whatever f of a is, that is going to be really, really close. We're not going to use an equal sign. We'll use a congruent sign, or a very close to equal sign, the squiggly equal sign here. Very, very close to whatever the linearization is at a. Okay, so the point x equals a is called the center of the approximation. All right, because it's you kind of think of it as the center of the tangent line. Why is this useful? Well, we're going to do a couple examples where I show you where it's useful, but it was more useful, like many things in unfortunately in high school math, it was more useful before calculators. All right, so let's do an example. I'll show you why that is the case. Okay, oh, there we go. All right, so let's do number 1 here. Find the linearization of f of x square root of 1 plus x at x equals 0. All right, so for the linearization, we need 3 things. You can see there's 3 parts over here. There's f of a, f prime of a, and and a. If I get all of those 3 things, then I get the line, the linearization. Okay, so let's make a list of all that stuff first. So what is a? Well, a is 0. That's the point that we're trying to get the linearization equation for. What is f of a? Well, f of a is equal to the square root of 1 plus 0. Well, I should say, shoot. Sorry, let's fix this. This is equal to f of 0, which is equal to the square root of 1 plus 0, which is just 1. And then we need f prime of a. F prime of a, well, we can figure that out real quick. F prime of x, we can get the derivative of this. This is just 1/2 of 1 plus x to the negative 1/2. F prime of 0 then is going to end up being just 1/2. Okay, so that's f prime of a is, and will be 1/2. And these three things allow me to get the linearization of f at a, or at 0 in this case. All right, so finally we'll write that L of x is equal to 1 plus 1/2 times x minus 0, which ends up just being 1 plus 1/2 x. So who cares? Well, let's jump over to number 2 and see if we can't apply this, okay? We want to use the linearization in number 1 to approximate the square root of 1.02 without a calculator. How close is it to the actual value? All right, so if we want to know what the square root of 1.02 is, based on what we figured out here, you can see that if I rewrite 1.02 in this way, if I write it as 1 plus 0.02, then it fits very nicely. It looks like the function, right? And in the function, I would have replaced x with 0.02. In other words, my a value, or the x value where I'd be evaluating it at, is 0.02. So if I want to know the approximate value of this square root, I can just find L of 0.02 and plug it in over here. Because again, what we're saying is that really, really close to whatever value a is here, so really, really close to 0, the linearization, the tangent line, is a really good approximation for function values. So I'm going to plug 0.02 in here. By the way, this would be equivalent to f of 0.02, in case I didn't make that clear. All right, so I'm going to try and get a good approximation of f of 0.02 here. So I plug in 0.02, I get 1 plus 1/2 times 0.02, and I get 1.01, okay? Well, how close is it? Well, 1.01, let's figure out how close it is. So if we take Desmos here, and we just plug in square root of 1.02, we got 1.01 for our approximation. The actual answer is 1.00995. So you can see that at 0.02, it's a pretty good approximation for the function value there at 0.02. Let's take a look. I have two videos I want to show you. I say up above here at the top, explain these videos, but it actually works better if I do the example first. So let me explain these two videos here. They're very short, and they're Desmos graphs. I should have dug out the actual graphs probably, but here is the first one. So you can see I've got this function here, sort of an ugly function. Okay, now it appears to be working. Sorry for the technical difficulties. You can see what we've got here is we're zooming in on this curve, sort of an ugly curve, and what I'm going to type in is the linearization here. And then what you can see is once that tangent line is on there, that as we zoom in, the tangent line and the curve are very, very, very close to each other. Okay, so if I want to know what are values close to 0 here, then I can just simply take the equation of the tangent line, plug in the value, and get it. The same kind of thing is going to happen here. So I have f of x there, I have g of x as the linearization. And this is going to be sort of ugly here, but you can see that if I plug in f of 0.1 and g of 0.1, I got 1.2 and 1 for each one of those values. And then I can, the closer I get to 0 with the values that I plug in, the closer the values of f and g are, right? Which sort of makes sense. This is the equivalent to zooming in on the graph. So you have 1.05 zeros there, and actually g is equal to 1. So it's a very good approximation. Okay, so let's end that, make that stop. All right, let's jump over here. Let's do the last examples. All right, so find the linearization of f, which is cosine of x at x equals pi over 2. So you should give this one a try and see how it goes. All right, I'm going to work it out here for you then. We need to find a. A is equal to pi over 2. F of a is equal to f of pi over 2, which is equal to 0 when you plug in pi over 2 for cosine. And then f prime of a, well, what would that be? Well, that would just be, that would be sine of x, right, would be the derivative. So that'd be f prime of pi over 2. Sine of x is the derivative, so we're actually looking at sine of pi over 2. Sine of pi over 2 is equal to 1. Negative 1, excuse me. No, it should be positive 1. I'm sorry, negative sign. Negative 1. There we go. Okay, so that's all the information we have, or we need then. So now I can write the linearization out. 0 plus negative 1 for the derivative there, and then x minus pi over 2. Once you simplify this, you get that your linearization is equal to negative x plus pi over 2. Again, this is just a tangent line. You might think, well, why aren't you just calling it the tangent line? Why are we calling it the linearization? You're thinking of this as the linearization as not the end. Lots of times we're trying to find the tangent line, and that's it. Or maybe we're trying to use the tangent line when we're trying to find the derivative in some application problem. The linearization is more a tool to solve other problems. So like I'm going to jump over to number 4 here, and we're going to use my answer from number 3. I'm going to use the linearization to figure out what approximately cosine of 1.75 is and how close it is to the actual value. So what we'll do is take L of 1.75. We get negative 1.75 plus pi over 2. And let's hop over to Desmos and see. So we had negative 1.75, negative 1.75 plus pi over 2. And what we're going to compare that to, so pi over 2, you can see is 1.57. And if I plug in, which is, if I plug in cosine of 1.75, you can see that it's a pretty good approximation. And the reason for this, I guess I should say here, is that 0.75 or 1.75 is really fairly close to 1.57. So there's a little bit of error here at the third decimal place, but you can see that it's sort of close. So 1.57 is pi over 2, that's the A value. And then 1.75 is fairly close to that. That's what we're trying to use. That's why we can use the linearization to approximate the value there. And I think that pretty much wraps up the linearization piece of this lesson.